Hello, everyone. Welcome to pre-lecture 23. This is going to cover chapter 16.4 in our textbook, talking about Gibbs free energy. So just a reminder of where we've been. Last week, we talked about entropy a lot, particularly with the third law of thermodynamics, the Boltzmann equation that defines our entropy on an absolute scale, and essentially says that if we have a perfect crystal at 0 degrees Kelvin, our entropy will be 0. We also talked about different ways we could quantify entropy. So you can look at the standard entropy changes, which we can get the values for every chemical we would need from a table in our textbook, or it would be given to you. You can calculate the entropy change by taking the sum of the products minus sum of the reactants. We can also relate entropy and enthalpy. And so if we use this equation here where our change in entropy of the surroundings is equal to the heat of the surroundings over temperature, we should be able to substitute in essentially enthalpy here. And so we can relate entropy and enthalpy. What we're going to do today is tie in this third thermodynamic property called Gibbs free energy. And so Gibbs free energy can be quite difficult to measure for both the systems and the surroundings. But what it is a something that we can quantify that actually defines the spontaneity of our reaction with regards to both enthalpy and entropy. And so the main way we would do this is say that our change in Gibbs free energy is equal to our change in enthalpy. Again, that's delta H minus T delta S. And so T is going to be our temperature in Kelvin. Delta S is our change in entropy then, right? So what this tells us, what Gibbs free energy is the maximum amount of usable energy or work that a reaction can produce. And so if we want to know how much work a reaction can do, it is very important we know the Gibbs free energy, okay? With regards to what is spontaneous and what is not, we know that delta G values that are negative will be what we call favorable or spontaneous, whereas positive delta G values are going to be unfavorable or non-spontaneous processes. When something is favorable or spontaneous, we call it exergonic, whereas endergonic would be if it is unfavorable. And yeah, that is how we define it. So something to keep in mind, basically delta G, when it is negative, things will be spontaneous or favorable, okay? We can think about this like we think about enthalpy as well. So your reactants will start with a certain amount of Gibbs free energy. Your products will, in all likelihood, have a different amount of Gibbs free energy. And so if that change is negative, it is exergonic. It is positive, it will be endergonic, right? And so that is it's very similar to how we think about our Gibbs free energy, right? Within this equation then, we can actually figure out when a reaction will be spontaneous based on these thermodynamic values as well as temperature. And so kind of the two easy situations are when our enthalpy is negative, that is going to be favorable with regards to enthalpy, and our entropy is positive or greater than 0. We know that anything, according to this equation, anything with a negative enthalpy and a positive entropy is going to always give us a negative delta G, which is Gibbs free energy, which means that that reaction at any temperature is going to be spontaneous, okay? The opposite is true for this box down here in red, where if our enthalpy is positive and our change in entropy is negative, we know that we're always going to have a positive Gibbs free energy no matter our temperature. That process is going to be unfavorable or non-spontaneous, okay? Then we have two intermediate situations. So say, for example, our delta H, our change in enthalpy, is positive. It's an endothermic reaction, but our entropy is positive. In that case, we have to determine at what temperature the reaction will be favorable versus unfavorable. So again, if our goal is to get a negative delta G for a reaction to be favorable, we know that because our entropy is our favorable term and we have negative T delta S, at high temperatures, essentially the bigger we can make this part of our equation, the more favorable our reaction is. And so for this sort of situation, it would be spontaneous at high temperatures, but non-spontaneous at low temperatures, okay? And then the opposite would be true for our other situation where our enthalpy is negative. So this part of our equation is favorable, and our entropy is negative, where we would then end up subtracting a negative value, which means it would be positive or unfavorable, right? And so at that, in that sort of situation, delta G will be spontaneous or negative at low temperature, and then unfavorable or non-spontaneous at high temperature, okay? We can also represent this graphically if this dotted line represents 0, which would be the point where we cross from spontaneous to non-spontaneous according to our Gibbs free energy. Again, we have all of our values here and the different situations they can find themselves in, okay? And the thing that would be, of course, changing here is temperature in Kelvin, okay? There are some other ways to calculate Gibbs free energy as well, in addition to that one equation. So we can use the same sort of equation that we would use to calculate standard entropies, but instead of starting with entropies, we start with Gibbs free energy values. And so delta G standard is equal to the sum of, again, the number of moles times our Gibbs free energy values for the products, subtracting the sum of the number of moles times Gibbs free energy for reactants. And so that is, again, same sort of thing as our standard entropy calculation, but in this case, we're using values for Gibbs free energy instead. Because we're talking about spontaneity, we can also tie that to the favorability of a reaction, aka a reaction's equilibrium constant. And so delta G standard is actually equal to negative RT ln K. And this K is our equilibrium constant. So we can define the favorability of a reaction, not only in terms of what K is, but also what delta G is, okay? And we can also do that under non-standard or non-equilibrium conditions. And so when we are not at equilibrium, we are then using Q instead of K. And so our change in spontaneity, our change in free energy is going to be equal to the standard free energy plus RT and the natural log of Q instead of K. Those are the main ways that we can calculate our change in free energy, or Gibbs free energy is also what it's called. Hope that was useful. We can also think about this graphically. So for different situations, if K is less than 1 and we start here, we would have to shift our reaction towards the products. Towards the reactants in order to reach equilibrium. So our reverse reaction will be spontaneous. The opposite will be true, whereas if K is greater than 1, we'll have to move our forward reaction to be spontaneous, aka we will form more products. And of course, if K is equal to 1, we would get a chart that looks like this, okay? And so what we're trying to always do is minimize the amount of free energy, because that is when things will be spontaneous, okay? Right, I hope that was helpful. If you have any questions, please let me know or ask them in class. Thanks for watching.